All right, so we're talking about Chapter 5, free body diagrams. This is part 2. So force is equal to mass times acceleration. So what units is force? Well, we can figure out the units. This is equal to the kilogram. Remember, acceleration is a meter per second squared. So the force is actually a kilogram meter per second squared. Well, instead of writing that out all the time, we name that, and that's equal to a Newton. Named after Sir Isaac Newton. And that's why a Newton is always capitalized, where kilograms, meters, and seconds are not capitalized. So this is equal to a Newton, just N, 1 Newton, if this is 1 kilogram. So, remember I told you at the very first day that all the units that we're going to use in this class are either kilograms, meters, or seconds. And then we just combine them in different forms to get new ones. Newton is one of those. All right, so forces are in newtons. Okay, so that was a simple case. Let's do a free body diagram of something much more complicated. So let's do a situation where I have a block on an inclined plane. Simple enough. The block on the inclined plane, we want to do a free body diagram for this block right here. So over on the side, I'm going to draw my dot for my free body diagram, and then I'm going to put gravity, and gravity is going to be mg. Now, if you have more than one block, you have to put subscripts like m1, m2, ma, whatever you label them as, you'd have to change that. And then I say, what other forces are acting on that block? Well, I have to know more about the situation. Let's say the block is sliding down this inclined plane at a constant velocity v. Okay? Remember, velocity doesn't go on this. So the only thing that goes in your free body diagram is forces. So you don't put velocity over here. But that tells me something right there. Is that, first of all, coming from the surface, right here, there has to be a force coming from the inclined plane, which we call our normal force. And remember, a normal force is called a normal force because it is always perpendicular to the surface. And so in this case, our incline is this way, so the normal force is perpendicular to that surface. Okay? And we have a frictional force. Frictional force, remember, always opposes the motion. Opposes motion. So in this case, we have a velocity going this way, so the friction force has to be going that way. So you always have to look at which way it's going. Now it's a little trickier when it's not moving, when it's a static friction force. Then you have to say, well, which way is the frictional force? Well, it depends on which way it is trying to move. And that becomes a little trickier. We'll try one of those later. But this way, we already know it's moving. So we have a frictional force. Let me change colors here. Going this way. And I want you to write your frictional forces as small f, lowercase f, and then you have to put a subscript for what kind. And in this case, it's going to be kinetic friction because the object's already moving. All right, so those are the only forces acting on it. You notice the frictional force is always along the direction of motion. So in this case, it's moving down the plane, so the frictional force is up along the plane. It's perpendicular to the normal force. Okay. Now, how we're going to solve these is what you have to do is there's always 3 steps to solving free body diagrams. The first one is you create the free body diagram. Step 1. Create a free body diagram. The key to creating a free body diagram is make sure you don't miss any forces and all your forces are going the right direction. Then, step 2, place an axis in direction of travel, direction of motion, I should say, and take components of forces not already on an axis. All right? So this is why we had to learn about taking components in chapter 3 of vectors, because these are all vectors. So we have our inclined plane theta. So what I want to do here is the block is moving down the inclined plane. So I want that to be my x-axis. So I'm going to make this my x-axis. I'm going to make this my y-axis, perpendicular to that. It has to be perpendicular to that, right? X and y have to be perpendicular, because then they work completely independently. And then I look and I say, oh, well, my normal force is right on the y-axis, the positive y-axis. Friction is right on the positive x-axis, but gravity is not on either the x or y-axis. So I have to take components of it so that we have one component in the y direction, one component in the x direction. So what I'm going to do is I just drop a perpendicular from the axis out to the end of the arrow, and then this becomes my component in the y direction. So I'm going to redraw this so you can see it more clearly here. So the gravitational force is mg. But we want this component of the gravitational force right here. Well, I have to use that the angle here, this inclined plane angle, is this angle right here. Don't get confused. Students mess this up a lot and they put it in the wrong place. It does not go there. How do you know? Because what happens if I make this angle smaller and smaller? Then that small angle is going to go to 0. The normal force is going to go to straight up, right? So as I make it smaller, the normal force has to rotate up like this. So this has to be the angle. It can't be that angle there. I know that may be confusing to think of because it's a very spatial thing. Just remember it's always the angle between the y-axis and gravity. As long as you do it this way. Okay? Then this becomes mg cosine theta on this side. This is the component in the y direction, the negative y direction. On the other side, over here, which is really this side of our triangle right here, remember? But since we can put a vector anywhere we want, I want all the vectors so their tails start at the center. So this becomes mg sine theta up here. Okay? All right. So step 2, this is for solving force problems. Just follow these 3-step procedures and it'll work every single time. Students get in trouble when they try to skip them. They try not to do it the way I tell them, and then they wonder why they get the wrong answer. Just do exactly what I tell you to do. I think they're like, oh, they want to get an answer so quick that they want to skip through it. Don't. Drew your free body diagram, do the components, and then we do F net x and F net y. Remember, net means the sum. So you sum up all the forces in the x direction. So in this example here, F net x is going to be equal to positive friction minus mg sine theta. See, it's really easy. If you did this part right, then the net x and net y are really easy to do because all you do is look at your free body diagram and go, oh, I have that force and that force in the x direction. This is positive one, this is a negative one. And in the y direction, I have positive normal force minus mg cosine theta. That's all I have, is that and that. And that's why we put any force that's not on one of the two axes, we take the components of it so it is on the axes, then it allows us to do F net x and F net y. Very easy. All right. So far so good. Let's try another one, a little more complicated. Let's say I have a situation here. I'm going to use this board space, so just make sure you remember these. I will keep going over and over that you have to do those things in that certain order or you get in trouble. Let's say I have a situation like this. I have a block here, we're going to call this block B. And on top of it we have block A. Block A is tied to the wall with a rope. Block B has a rope in which a force is being applied. So somebody's pulling on the rope. So block B is sliding out with a constant velocity this direction. Block A is not moving because it's fixed to the wall. But to solve this, I have to have free body diagrams. I need a free body diagram for both block A and block B. So I need two free body diagrams. So block A and block B. So block A, here, what forces? Well, I always have gravity, so I have MAG. Notice I had to put the subscript A there, because we're going to have another free body diagram, we're going to have MB. And so that becomes critical. All right, couple of things here. When you have two blocks that are touching each other, between these two blocks is what we call a contact force. Okay? The force between these two is a contact force. Now it's just like a normal force, but we're not going to call it a normal force because both these blocks can be moving, right? Or in this case, block B is